So good morning. I'm very happy to be here and looking forward to many events this week. I hope you all are as well. So I'm going to tell you this morning about two subjects that are of current interest, mock and quantum modular forms. So this talk will be more of an overview, invite you into the subject, introduce some of the basic definitions and ideas. I'm going to tell you a little bit about the history and eventually tell you about some recent results in these subjects. And hopefully this will be a nice extension to some of the background you heard earlier about ordinary modular forms. So you notice that is up here in my title slide, but there are some extra adjectives, mock and quantum. So in general, these are fairly new topics. Mock modular forms were not formally defined in the literature until about 6 years ago or so, same as quantum modular forms, although their origins really trace back much earlier, almost 100 years ago. So I'm going to start with Ramanujan's mock theta functions. There's the word mock again, but followed by theta functions. So theta functions are examples of ordinary modular forms. And Ramanujan, back in around 1920 or so, wrote down functions called mock theta functions that were somehow not quite modular. I'll get to exactly what these are in a few moments, but first I want to tell you a little bit about Ramanujan. So here he is. You can see that he did not live a very long life. He came from a very small village in southern India called Erode. And he was largely self-taught as a mathematician until a bit later in his life. But he was not a very good student. He failed out of school and really studied mathematics on his own and worked as a clerk to support his math habit, essentially. If you stay here through the week and attend the film on Friday night, you will see a lot more about Ramanujan's life and his mathematics. So eventually, he wrote letters to professors at Cambridge. You can imagine what happened. Most of these letters were ignored. They're being sent from halfway across the world, and as I mentioned, he wasn't very formally trained, so he may not have been writing in the most formal language. But eventually, Hardy saw something in what Ramanujan was writing here. And he invited him to Cambridge, and essentially the rest is history. Ramanujan, together with Hardy and alone, went on to produce a lot of wonderful mathematics that we're still studying and continuing today. So, as I mentioned, he passed away in 1920, and just a few months before he passed away, he sent one final letter to Hardy. At this point in his life, he's back in India. And in this letter, he sent Hardy a list of some very interesting, curious functions that he called mock theta functions. So you can see in this quote here from his letter, he says, "I am extremely sorry for not writing you a single letter up to now. I discovered some very interesting functions recently, which I call mock theta functions. I am sending you this letter with some examples." So here's one example of a mock theta function. He called it f of q. And this is some strange-looking infinite sum. In the numerator, you see q to the n squared, this simple numerator. And in the denominator, this function is built using the q-Pochhammer symbol. And that's basically a q analog or a functional analog to the ordinary factorial symbol. If I were to write this out term by term, what you see are these rising polynomials in q. 1 plus q squared, 1 plus q squared times 1 plus q squared squared, and so on. If you want to see the formal definition of this Q cognitive symbol, here it is. Just multiply 1 minus a cubed j and let j go between 0 and n minus 1. So these are curious looking Q series, we call them. Here's another one, omega, as long as you note down. It's a very similar shape. Instead of n squared in the numerator, we say q to the 2 n times n plus 1. And then a slightly different looking 2 factorial in the denominator. And here's a third Mach theta function. Similar shape. And there are just a finite number of these, 17. So why were these of interest? I mean, somehow he called these Mach theta functions. Somehow they were similar to theta functions or ordinary modular forms, but how? Well, one of the main things that were studied originally with respect to these Mach theta functions were certain asymptotic properties. And I'm going to get to that shortly. Various combinatorial properties, and Q series or Q hypergeometric, as we like to call these types of series identities. So many people went on to study these funny functions. Just this finite list of functions were a subject of study for decades after Ramanuja passed away. So all of these mathematicians and more studied Mach theta functions from the time Ramanujan wrote them down through the present day. So let me just backtrack a little bit and tell you about some of the combinatorial properties and Q hypergeometric properties that these functions have before we talk about modularity. And to do that, I want to discuss integer partitions. Mach theta functions are intimately related to integer partitions. So this is a branch of combinatorics. It's also intimately related to number theory and modular forms. And it's a very simple definition to define. What is a partition? Well, it's basically a way to break an integer down, a positive integer down, into a sum of smaller integers. So just do this in an organized way. Write down the partition, the integer, in a non-increasing sequence. And if you want to keep track of all partitions, we have a function for that, p of n. So let me show you some examples on the next slide. There's one partition of 1. There are 2 partitions of 2. Pretty simple so far. 3 partitions of 3. There are not 4 partitions of 4. There are 5. And this is really a subject in and of itself that, again, has been studied for really centuries, dating all the way back to Euler, up into the present day. These mathematicians here in the bottom row, more recent mathematicians, continue to study partitions to this day. There are plenty more as well. So you can write down partitions and count them for the first so many natural numbers n. It's not too hard to write this down. 1, 2, 3, 5, 7, and so on. But this quickly gets out of hand if you actually try to think about how to understand integer partitions without some more mathematics. For example, this last number that's over 1 billion counts the number of partitions of 115. So 115 is a very small number. There are over 1 billion partitions of 115. So somehow we need a better way to keep track of partitions than just trying to write them all out. And this is where generating functions come into play. So what's a generating function? If you have some sequence, pick your favorite sequence, and write down really just an infinite series in the variable q with that sequence as coefficients. Simple way to keep track of your favorite sequence. Of course, you have to worry about convergence issues and so on, but general, most basically, you might want to just package your favorite sequence into your generating function. So the idea would be to study this generating function to get a handle on the coefficients. So what happens for the partition function? Well, we can write down its generating function in the variable q. So we see 2 partitions of 2. 2 is the coefficient of q squared. 3 partitions of 3. 3 is the coefficient of q cubed. 5 partitions of 4. 5 is the coefficient of q fourth, and so on. So here, all the way dating back to Euler, we have a very, very nice closed formula for the partition generating function. As long as q is less than 1 in absolute value, the partition generating function is a very simple expression as an infinite product. How would you see that? Maybe Euler had some deeper mathematics at his disposal, or
when you're doing the multiplication, that the 1 minus q minus expression minus q. So if you look at the plot and figuring out what those numbers have.
I think the idea, yes, we just expand out this product and count, essentially. There's some analysis involved. Again, you have to pay attention to convergence issues, but if you ignore that, just take each piece of that product, 1 over 1 minus q to the m for each natural number m, use the geometric series, and expand out and count. And if you want to scribble it down a little bit later, it won't take you too long to see that if you collect terms for some exponent n, you'd be counting the number of partitions again. So, with this nice generating function, mathematicians have gone on to understand some deeper properties about the event. And in doing so, actually, there's something extra special about this generating function. It's almost essentially a modular form, this infinite product. It's almost a modular form. So what are modular forms? Just a brief review. You saw this definition earlier, but one component of their definition is that they have to satisfy a certain transformation law. So my notation will be H is the upper half of the complex plane. The imaginary parts of these numbers are positive. And modular forms map from the upper half plane to the complex plane. And they obey some type of symmetry law with respect to the action of SL2 on the upper half plane. Okay? Perhaps they transform back to themselves. Perhaps they're invariant under such an action, or more generally, there's something that goes in this black box. So here I've got gamma be some matrix in SL2, and the action of gamma on some point in the upper half plane is A tau plus B over C tau plus D, where our matrix is ABCD. So in general, there's some weight by which this modular form transforms. And maybe there's a character. We allow characters in the transformation theory of ordinary modular forms. So just, we'll see some specific examples of these later. But in general, this number is going to have absolute value 1. And we're going to look at modular forms that might be of integer weight, but they also might be of half integer weight. And one of our most well-known examples of half integer weight modular form is literally equal, its weight is literally 1/2, is Dedekind's eta function. So if we now make a substitution Q is not Q anymore. Q is not just some complex parameter. Q is now a function of tau on the upper half plane, either 2 pi I tau. The eta function is defined as Q to the 1 over 24 multiplied by this infinite product. So that should look familiar. It's basically the reciprocal of the generating function or the partition function, other than this Q to the 1 over 24. So that's a very important connection, that this modular form encodes some information about partitions. Let me look at its reciprocal. So just to recall the transformation for the eta function, it transforms well under the action of SL2. So here I've written down how it transforms under the two generators of SL2Z, 1, 1, 0, 1, and 0, minus 1, 1, 0. And in the second line here, you'll see that it does transform with weight 1/2, the square root. Great. And I've used this notation zeta sub 24 to stand for the 24th root of the e to the 2 pi I over 24. Some complex number on the unit circle. So, to understand various aspects of the partition numbers, we can then study the eta function via this relationship here. So that's really a lecture, another lecture, or 2 or 3 or 10 in and of itself. I want to tell you about mock modular forms, but wanted to set the stage by first getting into a little bit into partition numbers. Because mock modular forms and mock theta functions are connected to other types of partition functions. So let's take a look here. I've now written down the generating function for the partition numbers in a slightly different way. Here I've written it down as a Q hypergeometric series, Q series. That expression should also look familiar if you remember a few slides ago when we saw the mock theta function f of Q. It almost looks exactly the same. So in general, Q series that are built using these Q Pochhammer symbols are called Q hypergeometric. So now we can write down 1 over eta. This is Q series. And Ramanujan's mock theta function in an extremely similar way. They barely differ. In the denominator of the generating function for partitions, or essentially 1 over eta, you see these Q factorials, 1 minus Q, 1 minus Q squared, 1 minus Q cubed, whereas with Ramanujan's mock theta function, it looks like 1 plus Q, 1 plus Q squared, plus Q cubed. So at least they look similar, but certainly just because series look the same does not mean they can carry the same modular properties. I mean, this is some type of suggestion that perhaps these functions are related in some way, but in terms of their modular properties, it's not necessarily a good way. It may or may not be, right? It might be a good place to start. They look the same, but it's not necessarily a guarantee. So what about partitions and mock theta functions? Here's where partition ranks come into play. So this is another partition statistic, as we call them, called the rank. So if you take your favorite partition and take its largest part and subtract from that the number of parts, that's what we call the rank. Example, here's a partition of 10, and it has rank -1. So ranks could be any integer, negative, positive, 0. So this might look a little bit artificial, right? To say, well, partitions are pretty natural. You could imagine just thinking about counting and wanting to know the number of ways to break down a number into smaller sums. That's a very natural concept, but what's going on with this rank? It might look a little bit artificial. It turns out, actually, that the rank has some very deep properties attached to it. And it was used to explain certain congruences for the original partition numbers P of n. And that's part of a separate lecture series, but just to say that this function is very natural, as it turns out. And it turns out that this mock beta function f of q, if you expand it as a q series, select terms, its coefficients count differences in ranks. So the coefficient of q to the n in the mock beta function f of q is the number of partitions of n with even rank minus the number of partitions of n with odd rank. So that's another similarity to ordinary partition generating function. So let me summarize some of the things that have gone on in the last few minutes in this table. We have, in the first row, a modular, combinatorial, Q-hypergeometric function, all three in one. In the second row, we have this mock modular form f, which is combinatorial in a similar way to 1 over eta. It's also Q-hypergeometric in a similar way, but I have not addressed its modular properties at all. And this is, in fact, a very deep question that persisted for many decades following Ramanujan's death. What exactly are the modular properties, if any, of these mock beta functions? Phrased another way, a major question that we sought to understand is what roles the mock beta functions play in the theory of modular forms. Okay, so I want to tell you a little bit more about mock modular forms, mock beta functions, and eventually quantum modular forms. And as I explain some of these ingredients and results, I'm going to be speaking interchangeably about two domains that are equivalent. If we think of a function as a function of tau in the upper half plane, okay, well, here we are on the left side of the slide in the gray shaded region. And on the boundary of the upper half plane, we have rational numbers or cusps, which you heard a bit about earlier this morning. On the other hand, if we think about these functions as functions of q, under the mapping tau goes to e to the 2 pi I tau, that brings us to the inside of the unit circle in the complex plane, the other gray region. And these rational numbers map to the boundary. So just keep in mind, for the rest of the talk, we'll be interchangeably thinking about functions on the upper half plane, or maybe points on the boundary, these cusps, or functions of q inside the unit disk, or at certain roots of unity on the boundary. So let's go back to Ramanujan's last letter party and talk a little bit about more what he did in this last letter. So, in addition to writing down his list of mock beta functions, he also looked at the asymptotic properties as functions of q as these functions approach roots of unity on the boundary of the unit disk radially. So start from inside the unit disk, asymptotically understand these functions radially as q heads toward a root of unity on the boundary. Why would you need to asymptotically study these functions as you approach these roots of unity? Why can't you just plug in q equals I for the root? Okay, you have a problem. You have a singularity, right? In fact, this mock beta function f of q has a singularity on every even order root of unity. -1, singularity, I, singularity, and so on. So it's of interest, of course, to understand how functions behave at their singularities. This is why Lozano is studying these functions asymptotically. And he posed a question. He said, must Eulerian series with similar asymptotics be the sum of a modular form and a function which is O of 1 at all roots of union? So what's he saying here? He's saying, let's think about a few words that show up on the slide. Eulerian. By Eulerian series, he means Q hypergeometric, some type of function that looks like f of q or the generating function for partitions. So if you study some Q hypergeometric series that has similar asymptotics to a modular form, a true modular form is what he means, does that mean, if it behaves like a modular form in its singularities, that it's actually equal to a modular form plus some function that's bounded? That's a very interesting claim. If it smells like a modular form, is it a modular form? Plus something that's bounded at these singularities. Well, he didn't actually answer his question, but he says, the answer is that it is not necessarily so. I have not proved rigorously that it is not so. I have constructed a couple of examples. So he seems to say not necessarily. And this is what he's getting at in this investigation as to what these mock theta functions are, and why he's calling them mock theta functions. So he says I've constructed a number of examples. Actually, he constructed one example only.
The number is one.
Well, one is better than 0, I suppose. So what did we do? We wrote down a modular form. So I wrote it down in this funny way, because this is closer to how Ramanujan actually wrote it down. In fact, he wrote it down in longhand. He wrote down 1 minus q, 1 times 1 minus q cubed, dot, 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 times, and then he started writing down the first few terms in the sum. But in more modern terminology, we recognize this infinite product as a quotient of eta functions, and therefore a modular form. And this infinite sum is a modular theta function, which you can also write in terms of the eta function. So this is what I would prefer to write down like this. It's essentially eta cubed over eta squared to the power. So that's a nice modular form of weight and half. So he looks at this function b, and he makes this claim for his example in his last letter to Party. If q radially heads toward an even order root of unity of order 2k, then the sum or difference between f, the mock theta function f, and the modular form b is bounded. So let's say this again. If you have an even order root of unity at order 2k, then you either add or subtract the modular form b. And as q tends towards that singularity of f, that sum or difference will be bounded. Why does that not answer his question? It almost seems to actually indicate a positive answer to his question. There's one very subtle thing happening in the slide that shows that Ramanujan does not contradict himself. It's this minus 1 to the k. Technically, there are two functions needed here to carve out these singularities. You need plus b and minus b. So there's no single function that can do the job. It's close. So there is some relationship to ordinary modular forms via claims and this example in Ramanujan's last letter to Hardy. And again, I mentioned earlier that many mathematicians went on to study these mock theta functions after Ramanujan. But if we fast forward 67 years to 1987, precise understanding of how these mock data functions fit into the theory of modular forms was not yet achieved. So Freeman Dyson, he is the person who defined the partition rank function that I mentioned earlier. He's done many other things in his career, but he's the person after which became the rank function relevant to this talk. And he proclaimed decades after Ramanujan's death that these mock theta functions remain a challenge for the future, in particular understanding their modular structure if they move. So let's fast forward a little further to 2002. Finally, in this subject, there was a major breakthrough. Sanders Vegers, who was a doctoral student at the time, showed as part of his doctoral work that Ramanujan's mock theta functions, no, they're not modular forms, but they could be what are called completed to form something that transforms in the right way. So what he did first actually was package these mock theta functions together in vectors and produced functions that, after adding some non-holomorphic piece, would then transform like a vector-valued non-holomorphic modular form. So I'm going to show you an example of this on this slide. So he took f and omega, if you remember these mock theta functions, and packaged them together in a three-dimensional vector. So certain changes of variable need to be made, and certain multiplications by appropriate powers of q. But this turns out to be, well, half of the right object to study to get something that transforms in the right way. The other half is this beast, if you can call it that. This is a three-dimensional vector of what we refer to as period integrals. So this is a non-holomorphic function. And what are we integrating? Well, in the numerator, we have some weight 3/2 modular forms. In fact, they're theta functions. And in the denominator, we have some square root function. So it turns out when you add this non-holomorphic vector of period integrals of modular theta functions to that vector of mock modular forms, this vector of mock modular forms is very clean, it's nice and holomorphic. Now we're adding this rather messy-looking non-holomorphic function, but that corrects the error